The last couple of classes we've looked at equations of motion in the rectangular component system, so x, y, and z directions. So today we'll continue with equations of motion, but we'll use our second coordinate system that we've looked at, normal and tangential. And as you'll recall from your kinematics, the normal and tangential directions are defined by these two unit vectors. The tangential component, as the name implies, is going to be tangent to the path, and the velocity of the particle is going to be in the tangential direction. The normal direction will be back toward the center of curvature. And so, as we recall, even if a particle is moving at a constant speed, it's still going to have a normal component of acceleration. So our equations of motion in those two directions, in the tangential direction, we sum forces in that direction, set it equal to the mass times the acceleration in that direction, and similarly with the normal direction. Now, the tangential and normal components, as we saw in that sketch, define the plane of motion of the particle. And so we can still sum forces in the third direction. We call that the binormal direction. But since there's no motion in that binormal direction, then the sum of the forces has to be equal to 0. So we still sometimes will have to sum forces in that direction, in particular if there's friction involved on a particle that's moving in the normal tangential plane. We might have to sum forces in the binormal direction to find the normal force and relate that to friction. Now, one thing to keep in mind when you are working problems with this system is make sure that when you sum forces, you do it with the positive normal direction being toward the center of curvature. And we'll show you a couple of example problems of what we mean there. So in this case, this car is going over the crest of a hill, and we want to find the normal force between the car and the road. Now, you know from experience that as you go over a hill like this, that if you go fast enough, you could actually make the car leave the road. So you expect the normal force to be less than the weight of the car. Now, again, notice that the radius of curvature, so the center of curvature is going to be downward in this case. And so when we draw the free body diagram showing the weight and the normal force, and when we get ready to sum the forces, remember that the normal direction toward the center of curvature in this case is downward. So summing the forces in the normal direction, weight will be positive, the normal force will be negative, and we set that equal to the mass times the normal acceleration, recalling that the normal acceleration is v squared divided by the radius of curvature. Solve that for the normal force, and we get the weight minus the mass times the normal acceleration. So as we know from experience, the normal force is going to be less than the weight of the car. Now let's flip that around. Now the car is going through a dip, and so our radius of curvature is as shown, and the center of curvature now is going to be above the car. So our normal direction is going to be upward. And so we have a same free body diagram, but again the normal direction is changed. It's now upward toward the center of curvature. So when we write the equation, sum of the forces in the normal direction, well, now the weight is going to be in the negative normal direction, whereas the normal force is going to be positive, just the opposite of what they were previously. And so when you solve for the normal force, you find that it's the weight plus the mass times the normal acceleration. So as we know, the normal force is going to be greater than the weight when you go through a dip like this. So in the next class, we'll wrap up the equations of motion, and this time we'll look at cylindrical components. Again, the motion may be in plane, in which we'll say, okay, that's their polar coordinates, but we'll still want to sometimes sum forces in the third direction, which is the z direction, even again if the motion is only planar. And we'll probably look at least one three-dimensional problem, in which case we'll use all of our components the radial direction, the transverse direction, and the z direction.